University of Paris. And he will talk about uniform row algebras of, now I forget what ULF stands
Uniformly
for.
locally finite.
Uniformly locally finite metric spaces are rigid.
Okay, thank you. And thank you, Karen and Getlab for inviting me to Prague. It's very nice to be here. All right, so that's the title of my talk. As you can see, there is a long list of co-authors. This is because this is part of one of these square projects. It's really kind of similar to research in pairs, but it's in the US. And we had our first meeting last year, which happened online in like the 6 different time zones with a number of kids that was like often higher than the number of people in the Zoom meeting. So it was a very frantic week. Yet we managed to get a theorem out of this week of Zoom. So I'll report on this, and well, we'll have one more meeting this year. So hopefully we'll meet in person. Anyway, so uniform row algebras of ULF metric spaces. Well, this talk is really like in between operator algebras and coarse geometry. I was trying to find a good definition of coarse geometry. And so I opened the Piotr Nowak and Golang Yu book, and I read the preface. And this is what they say. So they say that large scale geometry is the study of geometric objects viewed from afar. For example, when viewed from a greater distance, the Earth looks like a point, while R is not different from Z. In the past decades, mathematicians have discovered many interesting and beautiful large-scale geometric properties, which have important application in topology analysis, computer science, and data analysis. And many classical notions in mathematics can be rephrased from a large-scale geometric point of view. So, because of this, I think that the study of coarse geometry is kind of important and interesting. And we try to understand it from the point of view of a system optimized. So let me just give you a couple of definitions. I will define what these guys are, these uniform row algebras, and I will define this uniform locally finite thing that I wrote on the board. And then I will also define what do I mean by rigid. Okay, so the main theorem essentially. This is a statement of the main theorem, but I have to say what these words stands for. Okay, so as I said, coarse spaces or large-scale geometry are like I study a metric space, but I don't care what's happening between close points. I only care like when I walk in the back, and as Piotr and Golang were saying, the Earth is a point. And the reals are the integers, or R to the n, it's really nothing but Z to the n, because if you walk back and back and back, you will just see the dimension, and you will not see that there is a space between 2 points. So these gets formalized by the following definition. So let X and D, XD and YW, oh, maybe the other chunk is actually better. Yeah, I don't know. All right, and Y delta metric spaces, B metric spaces. What are the maps that I'm going to care about? So a map from X to Y, it's said coarse. Coarse. If it sends close points to close points. Okay, so that means the following. If for every R, there exists an S, such that if I start from 2 points which are close, then the images are close up to S. Okay, so the distance, now I have to compute the distance in Y, in f of X and f of Y is less or equal than S. So for example, this means that if you have 2 lines, X contains 2 lines, let's say that they go to infinity, you can't send them to 2 lines that do this. Okay, this is not allowed because I want that points, pairs which are close, they stay close. Okay, by a factor that is determined at the beginning. And then, so this is sending close points to close points. And then I also would like to send far points to far points. So I have to be careful with quantifiers here, but this is the notion of expanded expanding map. So a map is said to be expanding if, which one is this? For every S, there exists R such that if I have 2 points which are far away from each other, then, well, they get sent to a distance which is B, okay? So this might be confusing because I'm putting S first and R, but once you read it and you internalize it a bit for like 30 seconds, you realize this is essentially saying that I'm sending far points to far points. And this is saying essentially that you can't send these 2 lines to 2 parallel lines which are close, okay, or to any close, because these pairs of distances which go to infinity, so the distances of the prey image should go to infinity. Okay. Okay. Expanding, I think, or expansive. I think you're right. I think it's expansive. I think you're right. Okay. Oh, well, I got more blackboards. And then I call a map which is both coarse and expansive, no expanding. I call it a coarse embedding. Okay. So a map F is a coarse embedding. If it's coarse plus expanding. Yeah. Okay. So notice that this needs not to be like injected. Because, for example, if you take a metric space which has 5 points and a metric space which has 1 point, then just sending a point, I mean, or collapsing the 5 points to the single point, that's a coarse equivalence. I mean, it's a coarse embedding, but it's actually furthermore, it's a coarse equivalence. So I say that it's a coarse embedding, it's a coarse equivalence if the range is dense in some sense. Okay, so suppose that for every y in y, I can pick a point, or suppose that there exists R such that for every y in y, I can pick a point in x, which gets sent such that the distance between f of x and y is less than R. Okay, so I have a single R, and the image, basically I'm saying that the image of x forms a net, okay? Then, which means that it's dense enough. I call this a coarse equivalence. Coarse equivalence. There are different definitions of coarse equivalences. For instance, you can ask for a map to be coarse. I mean, you can also write it this way. You can ask that F is coarse, so close points to close points, and that there is another map from y to x, okay? Plus there exists a coarse G from y to x, such that when I look at F after G, so here I'm going from y to y, well, I'm not really too far from the identity. So I'm close to the identity. Close to the identity on y and the other way around. And by close to the identity, I really mean that if I look at the soup between x and, let's say this one, g of f of x, and I soup over all elements of my space, this is a boundary. Okay. So when I go forward and come back, I don't fall too far from the tree. Okay. So you can equivalently, if you have an f such that there is some sort of coarse inverse, then f is a coarse equivalence. This is another way of defining this. And well, okay. Furthermore, I say that f is a bijective coarse equivalence if it's a coarse equivalence and it is bijective. Okay. So the definition, I don't think it needs to be spelled out, but you could be bijectively coarse equivalent. And two spaces are coarsely equivalent if there is a coarse equivalence between them, and bijective coarse equivalent if there is a bijective one, of course. So let me just give you a couple of properties and a couple of examples. So let's see. All right, so first of all, notice that course equivalence does not imply bijective course equivalence. Even when the spaces are easy. I mean, you can see this if you take the integers and the reals, because they have two different sizes. Or if you take a space with 1 point and a space with 2 points, because they have different sizes. But even for infinite spaces, this is not going to be the case. For example, let's see, what can you do? Yeah, so consider the set of pairs. Let X be the set of pairs which have the form I n square. So these are subsets of R2. For I less or equal than n. So basically I have 1 point, and then at 4 I have 2 points. Well, you want to include 0 in the networks. So. And then at 9 I have 4 points, and so on and so forth. Now, if you just add one single point here, if you just take y equal to x union a single point here, okay, the metric is the one induced from R2. If you add 1 point, these spaces are course equivalent, but you cannot find a bijective map that does the job. Okay, so these spaces are going to be course equivalent, but not bijective course equivalent, even though they look really the same. Okay. So these two concepts are not the same, but close by. The second thing, which basically I already said, or that you could have figured out, is that if you give me a space, a metric space D, and you consider a subset of X, which is a net, okay, and R net is dense for some R. So being a net, let's say it is an R net for some R. Where R net, it really means this, right? For every y in y, well, the other way around. For every x, I can find a point in y, which is R close to it. Then x and y are closely equivalent by simply choosing. You pick a point x and you choose the closest point, which is in y. And this is a course equivalence. Okay. So this is, well, then x and y are coarsely equivalent by picking, just picking points, picking for each x the closest point in y. And this says basically that if I have like a space such as, I don't know, this is very useful for applications to Riemannian manifolds, because I can discretize them, and then I can get a metric space which is some sort of discrete, okay? And then I can work by using this discretization of the manifold instead of the manifold itself, which is, at least it allows me to get away with the techniques that we are developing here. And a further example is given by groups. Okay, so you start with a finitely generated group. So S is finite. And then, I mean, this is more general on graphs because you have the shortest path metric if you have a connected graph. But for the applications, it's really group theory, which well, beneficial. We received benefits from the study of course geometry. So from here, you build the Caligraph. So I guess you're all familiar with the Caligraph. So what do you do? Well, the set of vertices is given by the elements of the group, and I join two vertices. I put an edge between them if there is an element of S which conjugates. Okay, so this gives me a graph. And it turns out that with the shortest path metric, this is a metric space, and then you can see this as with techniques from course geometry. And notice that these spaces, indeed, they have a particular property, which is one we're going to need a lot. In particular, it has the property that, let's see, there exists R, well, for every n, there exists R such that for every G in the group, when I look at the ball around G of size n, well, this has size less or equal than R. Okay, so not only the balls are bounded, they're finite, but they're uniformly bounded. All the balls of size 15 are bounded by a given R. This R, I think it's 2 to the size of S or something like that. Okay, it depends on the generating set, but it doesn't matter as long as this is finite. This condition is a condition that we have in this case, that we do have on discretization of Riemannian manifolds, and that we have in most interesting cases which are apt for applications, and therefore we should isolate it and assume it, because we can build sister algebras using this. So this is the definition essentially of ULF that I have up there. So let's see, a metric space is ULF. This stands for uniformly locally finite. If metric, that's D, if for every R greater than 0, when I look at the size of the balls of radius R, well, this is fine. Okay, so I have a uniform bound on the size of the balls. So this is uniformly locally finite. This is the property that we like to keep. And let me just say one more thing, that in general, considering large scale properties can be done for metric spaces, but can also be done more generally for coarse structures. And it turns out that if you axiomatize coarse structures in the proper way, the ones which are coming from metric spaces are the ones which are countably generated. And as a set theorist, the ones which are not countably generated are very interesting, but the kind of techniques to analyze those spaces are quite different there, because cardinals pop out, and then you have to deal with set theorists and talk to them. So maybe some of you will not like that. Some others will. No. Oh, okay. So we have our category of spaces. So we want to study uniformly locally finite spaces, and we have our maps between them, these coarse equivalences that I described there. And now I would like to show you how, well, one of the probably infinitely many ways in which rho associated an algebraic object to these metric spaces. And then I would like to talk a bit on what kind of properties are seen by these algebraic objects. So uniform rho algebras. So these kind of algebras were introduced by Rho for index theoretic purposes, but nowadays are useful for many things, like in the study of K-theory, or the study recently, actually, Meyer and Ewert, they had a very nice paper on Rho algebras and topological phases of matters. So with applications to mathematical physics. It's a great paper. I don't understand too much of it, but the Rho algebra part, it's quite easy to understand once you study these things, and it's quite interesting. So that's a very good application, the one they found. Okay, so let me just notice one thing. If you have a ULF metric space, it's countable. Okay. So this is easy consequence, but we can keep it on the side. Okay. So what do you do when you have a countable set and you want to find a sister algebra associated to it? Well, you build the L2, it's little L2, you make it an Hilbert space. Okay. So this is just, well, I guess L2 of X, it's fairly known, it's a complex Hilbert space. And then you consider the operators on L2 of x. And then I'm going to try to consider certain operators which are somehow seeing the matrix, because so far I haven't considered the matrix so far. And so let's see a definition. If A is an operator in B of L2 of x, I define its propagation. Propagation of A, it's simply the supremum for x and y in x. And then I look at the distance between x and y, but I only consider those x's and y's on which A is non-zero. Okay? So such that the absolute, well, such that A of delta of x, now this is a vector in L2 of x, so I can apply the operator A, and I can see what's happening at the vector y. And now I take all those pairs for which this is not zero. Okay? I take all the pairs on which this is not zero, and I look at the distance between x and y for these operators. And now I get a real number. Okay? Or infinity. Maybe I get a real number, maybe I get infinity. But nevertheless, I can consider all of those operators which have finite propagation. Okay? So now I take the operators of finite propagation. Notice that, for example, all compact operators, well, it's not true that all compact operators have finite propagation, but if you fix a finite subset of x and you look at all elements which are zero outside of that finite subset of x, well, then this has finite propagation because finite subset have finite diameter. Okay, so operators of finite propagation, they form an algebra. Form an algebra. Actually, it's a star algebra. What people like to do now in this case is close it up. So I close it in norm. And I define the uniform row algebra of X is just the norm closure of the algebra of finite propagation. Okay. In norm. All right. Okay, so this is the algebraic object we're going to consider. Now, let me just give you a small drawing of what operators are there. So in B of L2 of X, operators, you can see them essentially as matrices of complex numbers. I mean, not all of them, but these can be viewed as matrices indexed by X times X. Okay? Here you put the complex number which corresponds to this inner product there. And then different matrices will give you different operators. Not all matrices will give you a bounded operators, but certainly if you have like a bounded operator, you can find a matrix. And these operators, the finite propagation ones, are also known as banded. Because if you think that X is the naturals and the distance is our lovely distance and the usual distance, then you're really considering all of those operators which are non-zero only inside a band. Okay, you write a band there, and if you are only non-zero here, you have finite propagation because the distance is going to depend on the amplitude of the band, the propagation. Now, for different metrics, of course, this is quite nice to see at the beginning, but different metrics will give you different bands, which are way more difficult to draw and also more complicated to analyze, I have to say. But this is more or less the way you should see this thing. Okay. Now, given this, there are at least three properties that we can isolate. Let's see. Okay. Well, first of all, as I was saying, since when you give me a finite rank according to the classical base matrix, well, that's contained in a band. Just take a band which is large enough. So for this reason, the compacts are there. The compact operator on L2 of X, it's an ideal, in fact, of C star U of X. Okay, so you get all compact operators there. The second feature is, well, what is the smallest possible band you can consider? The band of amplitude 0. So this gives you the diagonal. So you do have this lovely copy of L infinity of X inside this sister algebra there. And furthermore, and this is going to be important in the proceeding. Furthermore, this copy is a maza. Well, it's a maza in B of H, but it's a Cartan maza. Okay. So you have a nice conditional expectation onto it, and all of the conditions in the normalizer. It's unital, so the approximate unit is definitely there. But it is a Cartan maza. Okay. And lastly, well, it follows from this that this algebra is far away from being separable. But at least you can see it as a countable union of subspaces which are closed in strong operator topology. So it might resemble a von Neumann algebra, even though it's not. It cannot be a von Neumann algebra because it contains the compact. Okay. So if you consider, let's say that if you consider you fix n and you take all operators of propagation less or equal than n, well, this is strongly closed, weakly closed even. Okay. So and in particular, Cu of X it can be viewed as a countable union of subspaces which are weakly closed. Okay, then you gotta take a norm closure. All right. So it's not a von Neumann algebra, but it's not far from being a von Neumann algebra, and this can be helpful for future things that we will try to do. So okay, let's see, where am I? Oh yeah, let me just give you one more. Well, let me just give you an example or two, and then one more property effect. So the first example you can see, it's like, okay, what if X is finite? What if X has 1 point? Well, then the algebra L2 of X is the complex numbers, and in the algebra is the complex numbers. But if X has 2 points, well, what you get is the M2. Right? So you get M2 because you get all operators, because I mean it's a bounded metric space. If X in general, I mean, if you have n points, yeah, I mean. Okay, but the more interesting case is the one of groups. So can I relate the uniform row algebra that I get from the Caligraph of a group with known constructions of sister algebras? Indeed you can. I have to admit, I don't know who proved this for the first time. There is a lovely proof in Brown-Lozawa, which it's a book that I would recommend to anyone. That essentially they prove that if you have L infinity of G and you look at the left translation action that you get from G just by unitaries, okay, by permuting stuff by letting G act on L infinity of G. Well, then you build the sister algebra, the cross-product sister algebra. This is precisely the uniform row algebra of GS. For any. Okay. So it doesn't really matter what point you take, what finite set you take. Okay. So this sister algebra here, you can see it as a cross product of a fairly natural action. Okay. Okay, so the goal of my talk and in general of this project, which is a project which has been started by Rufus, Willett, and Jan Spakula, I guess now maybe 10 or 15 years ago, is the following: what kind of information about the spaces can we get from information that we have on the algebras? Okay, so I guess we can write it like this. So the rigidity problem is the following. Let's say an instance of the rigidity problem. If C star U of X and C star U of Y are isomorphic, are, well, what can I say about X and Y? And let me just mention that you might wonder about also the converse question, okay? So if I know that X and Y are related by a course equivalence or by bijective course equivalence, what can I say about C star U of X and C star U of Y? Well, okay, so let's address this one first because it seems easier, and then we can go to the rigidity problem. So if you want to go the other way around, so if I have, let's say, a map, a bijective course equivalence between X and Y, let's say this is F, then in fact, I can extend F to a map between the two Hilbert spaces, okay? So I'm sending delta of little x to delta of F of little x, okay? So this is a map to the vector delta of F of x. And furthermore, this is a unitary. This is a unitary between L2 of x and L2 of y. And in fact, this extends to an isomorphism between the two system algebras. Okay, so this gives the fact that this is coarse, the fact that the map F is coarse is going to tell me that finite propagation operators will go to finite propagation operators. Okay, and the fact that this is expanding will actually tell me that all finite propagation operators in the domain, in the codomain, are taken by somebody in the domain. Because so far I have an isomorphism between the bounded operator of L2 of x and the bounded operator of L2 of y. I have to see that the image of C star U of x is actually C star U of y. But looking at the fact that this is coarse and expanding, well, you get that this is really not difficult to show. So this gives an isomorphism at the level of the algebras. And in fact, if one starts only with a coarse equivalence, one does not get an isomorphism at the level of the algebras. This is fairly obvious. For example, if you take the space with 1 point and the space with 2 points, because I mean the complex number and 2 are not isomorphic, but the spaces are coarsely equivalent. But what you get is isomorphism up to multiplicity. Okay, or in other words, Morita equivalence. So in fact, if x and y are coarsely equivalent, so if there is a coarse equivalence, then you do get that C star U of x tensor with the compact, it's in fact isomorphic C star U of y tensor with the compact. And you might say to me, but Alessandro, you said Morita equivalence, but only in the separable case is equivalent to being isomorphic when I tensor with the compact. Well, that's true, but also in this case. You can prove that Morita equivalence and being isomorphic after tensoring with the compacts are the same thing for these sort of algebras. Okay, so it's not only, it's a theorem, general theorem in the separable case, but here it works as well. So you do get up to multiplicity an isomorphism at the level of the algebras. Okay, so we now have to try to understand what's happening when we consider the other way around. And let me just say that, in fact, tangential, but related to this, not tangential, I guess, related to this question, there are many more. Like one can ask, okay, what's happening if I have an embedding of C star U of x into C star U of y? Do I get an embedding at the level of the spaces? What's happening if the embedding, it's an embedding into an hereditary C star subalgebra? Well, what do I get? Or even more, if you are a set theorist, in fact, you do that. What's happening if I have an isomorphism, but when I quotient with the compacts, when I consider the coronas? Well, do I get something at the level of the spaces? Actually, the answer to that depends on set theory. But I guess this is truly a different story. So there are many other questions that one can ask by modifying this sort of problem but I think today it's good to stick with the case of isomorphisms. And in fact, as George would say, where is the punchline? So let's write it down. This is the main theorem, which was again Florent, Braga, Elias, Anna, myself, and Rufus. Anna is Anna, which asserts that in fact you do get rigidity. Okay, even though it's not the best thing you can hope for. And it asserts, say X and Y are ULF metric spaces. Suppose that the two uniform row algebras are isomorphic. Then the sister algebras, then the spaces are coarsely equivalent and not bijective. Coarsely, well, we don't know. Coarsely equivalent. So we do get rigidity in the sense of coarse equivalence. We do not get bijective coarse equivalence with the current techniques. It actually proved itself to be a difficult problem, but well, we have another meeting of the square to attack that. And let me just say one more thing before. So I'm going to try to sketch some of the arguments behind that theorem. But let me just say that somewhat independently, even though with the use of similar techniques, there is a theorem of Braga, Elias, and myself who prove that if X has property A, or this is really an amenability condition. So this is equivalent to the uniform row algebra being nuclear. Okay, then in fact you get bijective coarse equivalence. You can from isomorphism, you do get bijective coarse equivalence. And in fact, one more theorem that I think I should mention before going on is that for coarse equivalence, we are capable to get an if and only if in the case when we tensor with the copy. Okay, so in fact, this implies basically the only part that was missing is that this implies that maybe sister U of X tensor compact it's isomorphic to sister U of Y when you tensor with the copy. Okay, so for the tensored version, we do have an if and only if with coarse equivalence. We do not know if there is an if and only if with bijective coarse equivalence so far. And well, we'll see what happens. But the plan is somehow to try to give you a sketch of the proof or of the main ideas. I guess I should pause in case there are questions or remarks. Yes?
A very simple question. Can the higher complex operators ever be complemented subspace?
No, I don't think so. I don't think so. But I should check. I mean, yeah, I wouldn't bet on it. No. It's somehow it's dense in weak operator topology, right? So I don't know. But... Okay. So let's see. Well, okay, let's start from the point where we left, where we said, like, if you have a bijective coarse equivalence, what do? You are really taking this copy of L infinity of X. Well, we are shuffling a base, essentially the base delta of X. You are shuffling it with F to the base indexed by elements of Y. Okay. In terms of operators, what you're doing, this is when you start from a bijective coarse equivalence. In terms of operators, you're taking this canonical maza, and you have an isomorphism from sister U of X to sister U of Y. And this isomorphism, phi, is sending the canonical copy of L infinity of X to the canonical copy of L infinity of Y. The image of the canonical copy of this measure, it's this measure, if I start from a bijective course equivalence. Because diagonal operators will be sent to diagonal operators. I'm just shuffling the base. Okay? In fact, if you start with an isomorphism that does this, you can get the shuffling of the bases out of this condition. So in case you start, in case, let's see, in case you know where L infinity, well, you know that L infinity of X goes to L infinity of Y, you're good. Because you take the minimal projection, chi of X. This is a rank 1 projection in B over 2 of X. You know that it has to go to a rank 1 projection in B over 2 of Y. But now you know that it has to go to a rank 1 projection here. And rank 1 projections there, they have the form chi of little y for some little y in big Y. And then you send X to Y and you check that it works. And this is a bijective cross equivalence. Okay, so if you know that this guy gets here, you look at minimal projections, you see where do they go, you look at the index of the minimal projection of the image of chi of X, this has to be some Y, you send F there. And well, then it's really algebra, easy algebra, to check that this is a bijective course equivalence. Okay, so this gives a bijective course equivalence. But in fact, when you stare at this fact, which is not so deep, you start drawing a bit. And what do you do? Okay. Essentially, you're trying to use the isomorphism and the information that the isomorphism is telling you about the minimal projections to guess where X has to go. Okay, you want to study these elements, their images, and they should try to tell you where the point X has to go because you want to build your function, okay, from the isomorphism. So in this case, in case where L infinity of X was going to L infinity of Y, well, essentially, X, this is Y, X, Y. Okay, so this point X, this is a diagonal. This point X, you were really sending it to a point. Okay, but now, and this point X, X here, you were sending it somewhere else. But the image phi of chi of X was leaving to you a trace of where to go. It was telling you where do you have to go. Okay, so let's consider the following set. In case this is not true, then you have to work a bit more in general. So let's consider the case where actually L infinity of X does not get sent to L infinity. Okay, so let me define the following sets. So for epsilon greater than 0 and X in X, I define the set Y X epsilon to be the set of all Y. This is a subset of Y. I'm trying to understand where does the projection phi of chi of X leaves a trace on this diagonal. Okay, so I'm defining it as a set of all Y such that the norm of chi of Y, phi of chi of X is big. Okay, so I fix my epsilon, I look at where phi of X is going, and okay, maybe phi of X is a matrix something like 1/2, 1/2, 1/2, 1/2. It's a rank 1 projection, it's here. Okay, maybe, we don't know. But then I put in this set these 2 points. Okay, the 2 points where I'm leaving a non-trivial trace. Okay, and now the point is the following, which is due to it's truly due to Spacula and Willett, which is the following lemma or observation. Let me just say that Spacula and Willett actually were the ones that, with the use of this, proved rigidity in the property A case. So they proved that from an isomorphism of the uniform row algebras, in case you have property A or nuclearity of the algebra, these are equivalent, you get coarse equivalence of the spaces. Okay, so the bijective part, it's a different technique. The first thing was done via this trick. So the following lemma. Suppose, okay, phi, it's our lovely iso. And now suppose that there exists a single epsilon such that for every x, the set y x epsilon is non-empty. Okay, so suppose that every x eventually leaves some sort of trace on the diagonal. Okay, then any map which sends x to an element, this is a subset of y, right? These are the y's where I'm leaving a trace to any element of y x epsilon is a coarse equivalence. Okay, so with this in hand, and again, this is not so difficult to prove. What you have to do is use your counter diagonalization argument. Just think about it, and if it's not true, just well, you want to prove it's coarse, but basically just show that you know that you have a projection here which swaps things. You have a partial isometry which swaps points, and this partial isometry needs to have bounded propagation in some sense, because it's coming from something that had bounded propagation. Okay, so the proof of this is really not so difficult once you put your hands on it. But I have to say that given this lemma, it all amounts to show that I can find my epsilon such that these are non-empty. The full rigidity proof amounts in showing that. But this can be tricky and difficult, and I mean it took lots of years of study, but it is related to the concept of, well, I guess it is related to the concept of ghost operator. So let me give you this definition. How far should I go? Until 5. Okay. Okay, then maybe no. Let me just say that a projection which might be in the range that will cause you problems, a lot of problems, is the projection. Consider the following projection. So consider Pn, the projection on n by n matrices, which has 1 over n everywhere. So this is a rank 1 projection, and it has 1 over n on every single entry. Verify this is a projection, it's rank 1, because, well, the image has 1 vector. Okay, and now put them diagonally, P1, P2, P3, P4, so on and so forth. If this projection, if the sum P1, P2, P3, P4, etc., so you say P is the sum of the Pi, if this sum here is in your uniform row algebra, this will cause you problem. And in fact, this is a prototypical example of a ghost. A theorem, a famous theorem of Higson, Laforgue, Scandalis, related to the study of the Bancon conjecture, showed that there is indeed a metric, which is a ULF metric on the naturals, such that this projection is in the uniform row algebra. Okay, this was done with the construction of expander graphs, which are highly connected graphs of regular degree, because you want to keep ULFness. Okay, so that P is in C star U of, I guess, n delta. Okay, so this one can get in the way, and this is a big problem. I mean, these and their modifications. Actually, she's pretty nice. The problem is like when you start modifying it and changing it too much, you will have a lot of issues. Because you see, if you think about this projection, like take the single ones, P1, P2, P3, they don't leave a trace. The trace that they leave, it gets smaller and smaller and smaller. For every epsilon, there is only a finite number of axes of naturals which leave a trace on points in Y, right? So if this is there, this is gonna cause you a lot of trouble. Nevertheless, we were able to avoid this, and essentially what we were capable of proving is that these projections can never be in the range of L infinity of X if your copy of L infinity is coming from an isomorphism of uniform algebras. Okay, and or in other words, position. Well, I guess you can say. Let's see. Okay. Is it ghost if for every epsilon, the set of pairs which A is big is finite. Is finite. It's a ghost because it's disappearing down. Okay, this is a ghost, for example. Okay, and the proposition is that in the setting of an isomorphism, then you don't have ghosts in the image of L infinity of X. Phi of L infinity of X intersection ghosts. It's only compact stuff. Of course, compact operators are ghosts. But here you only get compact stuff. And this basically says to us that eventually we are going to be able to pick. We are going to be able to find that these guys are non-empty for every X. So there is epsilon such that for every X, I'm allowed to find a set of entries on which I'm big, and then I can pick and I can find my course equivalence. So the corollary is the main theorem. To prove this, we used a theorem from economics, which is called the well, it's a theorem from convex geometry, but it was applied to math economics. It's called the Folkman-Shapley theorem. It talks about convex subsets of R to the M. It's a very, very cute result, especially when it's rephrased in terms which are not from economics, because you can understand them. Anyway, we do get course equivalence. Course equivalence from isos of row algebras. So I want to conclude with one more corollary and a couple of questions. The first corollary, it talks about groups. So, okay, we said it with Ilias and Braga, we were able to prove that if the space is amenable enough, you do get bijective course equivalence. In fact, if the group is exact, then the uniform row algebra of the group is nuclear, and these hypotheses there are satisfied. So for groups, in fact, we do get bijective course equivalence for amenable groups. For non-amenable groups, or non-exact groups, in fact, there is this result of Rufus and Stewart, White, really after the work on of Wyatt. Why? I know. I mean, these are two different people, as you can see from the spelling, obviously. Well, by looking at the theorem on amenable metric spaces, they were able to conclude a theorem on non-amenable groups. So they proved that if two groups, G and H, which are finitely generated, are coarsely equivalent, then they are bijectively cursive. And therefore, if we take our result and their result and we put them together, we get that for every finitely generated groups, bijective course equivalence and isomorphism of the uniform row algebras actually coincide. So there are three natural questions, which I'd like to leave on the board. But the first one, it's obvious, is like, what about bijective course equivalence? If you don't admit property A or regularity condition. Well, we don't know. The second question, it's really about instead of considering the tensoring with the compact of the uniform row algebra, to consider the row algebra. Now, the row algebra, and you might say, why all these names? I don't know. But the row algebras, it's done by matrices where instead of complex numbers, you play compact operators every time. And then you take finite propagation stuff and so on and so forth. Okay, so you're allowed to play compact operators. So you have an extra dimension. And it is conjectured that isomorphism of row algebras should correspond to course equivalence as an if and only if. We don't know that. It seems to be quite difficult because our Folkman-Shapley doesn't apply. That's the main problem. So what about, let's say, other row type algebras? And what do isomorphism in this case correspond to at the level of the spaces? And lastly, for those of you who like set theory, it's what about course structures, which are generated not only by uncountably many entourages, which give you metric spaces, but by uncountably many. We are able to conclude our result if you have size less than the least cardinal on which Martin's axiom fails. But whatever, it's a cardinal. So general, i.e. bigger course spaces. We don't know. We have some results with Braga for property A. Because we kind of know what to do when we approach it via countable submodels sort of ideas, but we have no idea what's happening in general. And I guess that's all. Thank you.
Thanks very much for the talk. Do we have any questions in the audience?
Row algebras are isomorphic. So you mentioned that L infinity of X is Cartan subalgebra of them. How about this Cartan preserving isomorphisms?
All of these isomorphisms are Cartan preserved because they're strongly continuous. Because essentially they come from a map from L2 of X and L2 of Y. Since you have the compacts there, well, the compacts have to go to the compacts.
Okay. Okay, then.
So this gives you a map from H to H prime, from L2 of X to L2 of Y, and this essentially you can use the condition expectation that you get from this map, and the normalizer condition it's okay, of course, and therefore it sends a Cartan to a Cartan. The problem is that we don't know where Cartan may sit inside. They can be skewed, which is a problem.
And okay, also, how about the twisted groupoid picture? Although you mentioned that is not separable.
Yeah, I don't
know.
I mean, the word groupoid and the word twisted groupoid are very far from my knowledge. So I don't know. I never studied them personally. Maybe it's a picture. So they're not separate. I mean, they're not countable. The structures you get.
Still, there are some things about non-separable case.
Yeah, I can remember. I'm separable most of the time. So,
In the work of Roth.
but I don't know. Yeah.
But here also I see there are some, for example, if you consider this J, then if J is countable, then we will not arrive to the separable fields.
I think the problem might be ULFness if you consider spaces which are not discrete, right?
Yes. This is,
And then if you lose ULFness, all of our techniques, you can take them from away. Probably so. I mean, they don't apply. So, I don't know.
thank you.
Other questions?
Yeah, okay. I know this is kind of a cliche question, but is there a non-commutative notion of cost equivalence? For example, like these, these compact quantum metric spaces of refill. Do you know what I mean?
I'm not so familiar. No, I don't know.
Okay.
I mean, probably. If you can quantum something.
Okay, is there anything that's really good saying in the relationship between course maps and continuous? I mean, the course continuity.
No, because continuity talks to you about local stuff, right? But coarseness talks to you about global. I mean, at infinity. These are properties at infinity. So you can build. I mean, I think the map between Z and the reals. Just whatever the smallest integer below. Sorry, smallest integer above or something, floor or ground, whatever. I mean, there you lose continuity brutally, and you can get nasty examples.
Category of topological spaces, and you're taking the category and you're putting a completely different set of morphisms in there to produce a new category. I mean, is there anything you could even say?
Because it's not the topology that interests you. I mean, the topology, it's a local thing, right? I mean, you want to see what's happening, what things happen in the local. Here, you want to understand what's happening at infinity. So you're really, yeah, I mean, these are topological spaces, but you don't care in some sense about the topology.
Okay, so then all of these equivalences is course equivalent to one. Then we can say very little about the relationship topology.
Yeah, absolutely. They don't talk about the topology.
So then in some sense, why don't you get rid of the topology?
Well, I mean, you keep the metric. You keep the metric because, but I mean, you can actually do this. As I said, you can define a course structure. So what is a course structure? It's no, I'm gonna make a mistake here. But, sure. I mean, the metric you keep it because it's useful for applications like groups and Riemannian manifolds and stuff like that. But in general, all right. So you want what? You want a collection of subsets of x times x. It's a bunch of these guys. It's dual to uniformity. So whatever. Okay. The diagonal is there. That's for sure. Such that the diagonal it's in E. And then you want it to be connected, but that's not necessary. But let's say it's connected. So all finite sets are there. Finite sets, and then you want it to be closed by subsets and composition. Okay. So subsets, and this you call a course structure, and you can say exactly the same. I mean, you can do exactly the same reasoning. The problem is, okay, so there is a theorem, subset plus composition. There is a theorem that says that this subset as a countable cofinal set for inclusion, if and only if you can put a metric on the space, such that the course structure that you get from the metric I mean, from a metric, what do you do is you put you fix R and you call ER all those pairs which have distance less or equal than R. Okay, and then you close it by subsets. This is already closed by composition once you close it by subsets.
Yeah, the metric giving you your core structure in the same way that you would metric would give you your topological space.
Exactly, exactly.
So you somehow you generalize, if you want to generalize a metric space locally, you look at topology. If you want to generalize a metric space globally, you look at core structures.
Yeah.
And then the results that you've stated, do they generalize to this setting, or you just don't know?
The problem is, okay, as I said, if it is a countable generating set, it's a metric space. If it doesn't have a countable generating set, we can say things at omega 1. I mean, then you need, you need to be a sort of a set theorist a bit. But there are things we can say. I think for property A, we basically get, so for things which are nuclear, we get some sharp results. For the general case, we haven't thought about it so far. I mean, we know we could try. It's in the plan, but you can say things. Yeah, but you know, even if you have a core structure which is countably generated and you take a substructure, that might not be countably generated. So things get nasty. Okay. Because you can play with ultrafilters there. Yeah, well, it's okay.
Maybe very stupid question, but do you know the relationship within instead uniform structure? This should be the dual, right? Of a uniformity.
Dualized.
And for uniformity, I recall that you can extend also the theorem you said. It is true that a uniform space is metrizable even only if you have a countable cofinal base that generates the whole uniformity, linearly ordered by inclusion. And but it's also true that if you have this linearly ordered countable family, which is linear ordered by inclusion, and is not countable, but it is, for example, of a certain size mu, then you are mu metrizable in the sense, I mean, with the extent. So it may be that maybe you can still use a kind of matrix, sort of generalized matrix, and but it was just.
I would bet yes. but it's a bet.
Okay,
I don't know enough about this. I mean, I know that these things exist and they generalize these sort of things. So I fear for uniform local finiteness, as always. It's because you want balls to be of finite size. So when you look at these metrics, since you want balls to be finite size, you really look at balls which are increasing and not decreasing. So you don't want like the distance has to be discrete. But I don't know. No.
As a metric space from the algebra symbol itself. So according to this theorem, then we don't want to actually force it null.
Can I construct a concrete representation?
Can you recover X out of the algebra itself?
Yes. In short, yes. So what do you do? Okay, it's a bit technical, probably, and I will make a mistake. But yes, I think this is in a paper of Willett and White. They actually do this. Yeah, well, Gelfand duality is a deeper result because Gelfand duality also asks you, are all automorphisms coming from maps, and what is the relation between maps that gives you the same automorphism? Yeah, it's a precise duality. We also have this for property A spaces so far, but because we don't have bijective cross equivalence. Once you get bijective cross equivalence, we are capable of proving complete duality. This is a paper with Braga, only Braga and me. But But for your question, yes, there is a specific way. But you know, it's in some sense, if you think about it, since these are countable spaces, these are really metrics on. You can see all of them as metrics on the naturals. So knowing X, it's a natural. It's the naturals with some weird metric, and this is what they get. But yeah, other things you can try to understand if you look at, for example, the nuclear dimension of the algebra. Can you get the asymptotic dimension of the space? Asymptotic dimension is a notion of dimension which works at infinity. Okay, and then there are these sort of questions like what kind of properties of the space can you see from the algebras in terms of topological dimension or well asymptotic dimension and stuff like that. And one interesting question is, can you see Gromov's exponential growths from the algebra? But yeah, I don't know. Should not. I don't think it should, because in the well, no, actually, no, because you see, tensor product cannot be a uniform algebra, right? Because you need to have, otherwise you will have a copy of the compact on one side and a central projections. I mean, well, not a central projection, but you have too many ideals in some sense. I fear. I never thought about it. Let me see. Yeah, I don't know on the tip. I don't know at the moment. Maybe yes. Yeah, I don't know. Because these have become 4x4 matrices. I mean, become matrices of size 4, and my head is too slow to think of matrices of 4 dimensions. But maybe there is a canonical map that I'm not seeing at the moment, either one way or another.
Any last questions? If not, let's thank Alessandro again. And next week we have Simon Lentner from the University of Hamburg, and that will be just on Zoom, so he won't be here in person. Hope to see you next week.